Welcome to the section on cost-sensitive learning. In this section, we're going to discuss what cost-sensitive learning is, what cost is and what types of cost should we consider, how do we actually obtain the cost, and what are the most commonly used cost-sensitive approaches. Let's dive in. You're probably familiar with most classification algorithms like naive Bayes, logistic regression, decision trees and other tree-based algorithms like random forests, gradient boosted machines, neural networks and so on. Most of these classification algorithms are designed to minimize the error rate. That is, these algorithms pursue to minimize the percentage of incorrect predictions. This is equivalent to saying that they seek to maximize the accuracy. So intrinsically, these algorithms ignore the difference between the types of misclassification errors. In particular, they implicitly assume that all misclassification errors have the same cost. Yet, in many real-world applications, this assumption is not true. In fact, the difference in the misclassification error can be quite dramatic. For example, in medical diagnosis, misclassifying a sick patient as healthy is more costly than otherwise, because the patient is at risk if they are not treated early or properly. So we can't afford really to classify a sick person as healthy. In insurance, for example, misclassifying a fraudulent claim costs more, and in particular more money, than wrongly classifying as fraudulent a legitimate claim. Cost-sensitive learning takes costs, such as the misclassification cost, into consideration. So cost-sensitive learning is a type of learning that takes the misclassification costs into consideration. The goal of this type of learning is to minimize the total cost, in this case, instead of the classification error, as most mainstream algorithms do. So the key difference between cost-sensitive learning and cost-insensitive learning is that cost-sensitive learning treats the different misclassifications differently. So to summarize, cost-insensitive methods, which include most mainstream algorithms or off-the-shelf algorithms as we take them from scikit-learn, minimize the error rate, whereas cost-sensitive algorithms minimize the cost of misclassification. Cost-insensitive algorithms assign the same misclassification cost to all misclassification types, whereas cost-sensitive methods apply different classification costs to different classes. We can visualize cost-sensitive and cost-insensitive learning with the help of a cost matrix. A cost matrix is a table, like the one that you see here, with the costs of making correct or wrong predictions. It looks pretty much like the confusion matrix we discussed in section 3. In this table, we have the predictions versus the real target. So when we predict 0 and the real value was 0, we have the true negatives. When we predict 1 and the real value was 1, we have the true positives. And in the diagonal, we have the false positive and the false negative rate. C of ij is the cost of assigning an observation of class j to class I. And in particular, z of 0, 0 and z of 1, 1 are the costs of correct classification, which in most cases is 0, whereas z of 0, 1 and z of 1, 0 are the costs of the false positive and the false negatives respectively, which in most mainstream algorithms is 1. Standard machine learning models use normally a 0-1 loss function, which assigns a cost of 0 to correctly classified observations, as we see in this diagonal, and a cost of 1 to an incorrectly classified observation, as we see in the other diagonal. Because this 0,1 loss function uses the same cost associated with the wrong classification for all classes, it is highly susceptible to skewed class distributions. This 0,1 loss function over imbalanced datasets can be easily minimized just by focusing on the majority class and overlooking the minority class. And this problem gets exacerbated as the imbalance ratio increases. So this is a bit similar to what we observed with the accuracy in section 3. We can predict that all observations belong to the majority class and we will get a high accuracy. In this case, the models can optimize predicting observations from the majority class and they will obtain a very good predictive power. Yet, what we are really interested in is in predicting the minority class. Cost-sensitive learning aims to alleviate this problem by adapting the loss function with different costs associated with the different classes. These costs can be seen as a penalty introduced during classifier training, or maybe in some cases during the predictions, as we will discuss later. And this penalty, or this cost, aims to increase the importance of classifying correctly those observations that are rare. By assigning stronger penalization errors on a given class, we force the classifier training procedure, which now is aiming to minimize the cost, to focus on instances coming from the rare observations. This leaves us with a question, which is how do we obtain the cost? And in fact, more broadly, what is cost? How many different types of costs are there? Which one should we consider? How important the costs are? And then, in practice, what are the different cost-sensitive approaches? We're going to explore all of this throughout the rest of this section. So let's crack on.